Great. Okay, so welcome everyone to lecture A.3. So today we are going to continue our study of the power of interactive proofs. And specifically today, we are going to design an interactive proof for every language in the complexity class PSPACE. So for every language decidable in polynomial space. So if you remember in the first lecture, we already proved an upper bound on the power of interactive proofs, right? We proved that if a language is decidable if a language has an interactive proof, then it is decidable in polynomial space. That gave this complexity class inclusion that told us whatever is the power of interactive proofs, it cannot exceed that of the complexity class PSPACE. And today we'll prove that this upper bound is tight. Specifically, we'll prove that every language decidable in polynomial space has an interactive proof. And in some sense, we have been sort of working our way up through various examples. First with an interactive proof for GNI, showing that interactive proofs are useful for something mildly interesting. And then thanks to the sum-check protocol, there was a rather direct application to prove that CoinP is contained in IP. And then with very little extra work, we were able to prove that P to the sharp P has interactive proofs. Now, P to the sharp P is contained in PSPACE, which is believed to be an even bigger class. And now we have, in some sense, reached the end of the journey on the power interactive proofs by, as I will see, by proving this theorem. Okay. And the approach is going to be very much inspired by the approach that we took in the last lecture. Specifically, we had this, you can think about it as a three-step recipe. First, we picked a problem that was complete for the class. For example, for CoinP, it was unsat, or for P to the sharp P, it was essentially sharp sat. We arithmetized it, and then we designed some protocol for the algebraic problem. So in the last lecture, the first step was choosing either unsat or sharp sat. Arithmetizing meant to reduce either of these problems to some sum-check problem, okay? And then we would run the sum-check protocol on that. Today, we'll follow a similar approach. Specifically, the canonical complete problem for PSPACE is something called TQBF. We'll dedicate an entire slide to recall what that is. It stands for True Quantified Boolean Formulas. Okay, there's many other complete problems for PSPACE, but this is the canonical one and the one that we'll use to arithmetize. So we're gonna arithmetize this problem, and we're gonna get, rather than a sum-check problem, we'll get some sort of, let's call it a sum product problem. Okay, and then we will see something called Shamir's protocol, which is the kind of the analog of the sum-check protocol, except that it is designed to kind of tackle this sum product problems. Okay, and together all the steps are going to give us an interactive proof for TQBF and therefore all of PSPACE. All right, so that is the plan for today. Are there any questions at this point? All right, so let's start out by talking about what is TQBF. And for that, we need to talk about what are quantified Boolean formulas, or today primarily is going to be fully quantified Boolean formulas. So let's start with an example. So they're essentially logical expressions that look like this. So you have some base formula, Boolean formula, the usual way, and prepended to it, you have a quantifier for every variable that appears in the formula. So in this case, it says for all x1, there exists x2, and there exists x3 such that this is true. Okay, so that's how to read this one, left to right. And of course, the order of the quantifiers matters. And this expression either evaluates to true or it evaluates to false. Okay, and we'll evaluate both of these. Another example is for all x1, there exists x2 such that for all x3, this expression is true. Okay. So more generally, you just have a Boolean formula, and every variable appears with some quantifier, either for all or there exists. Okay. And so let's go through these examples. The way you want to think about these is as trees. So if you're wondering, does this evaluate to true or false? Well, first I'm telling you, it is going to evaluate to true, and one way to check that is to basically write down kind of the tree that proves it. Now, for all x1, what does it mean? It means that we want the remaining formula to be true, regardless of whether x1 is 0 or 1. So we're going to branch out and say, okay, let's fix x1 to be 0 or x1 to be 1. All right. But then we have two existential quantifiers, so it's enough for us to find values for which fixing x2 to be something and x3 to be something for the x1 that we fixed will get 1. So for instance, here, I could say, all right, we have fixed x1 to be 0. It's enough for me to pick x2 to be 1 and x3 to be 1, such that this expression with the variables kind of replaced in, I get 1. Why do we get this? Because x1 is 0, so 0 and 1, that's x2, or x3, and x3 is 1. So we have 0 or 1, and that's 1, right? And below here, the same thing, because anyways, x3 was dictating by itself what the value was, regardless of what happens here. Okay? So we see that this expression is a true, fully quantified Boolean formula. Okay? This other example, turns out is actually false. Here is a tree for it. It's a bit awkward to see it this way. A more precise way to do it would be to negate the formula and checking that the negation is true. But let's still look at this exact formula. So we have, for all x1, it's saying, okay, we have the option of 0, the option of 1, right? Let's first go down the option of 1. If we go down the option of 1, if I fix x2 to be 1, it means that this end here of x1 and x2 is definitely going to be 1, like 1 and 1, 1 and 1, regardless of what x3 is. So kind of this whole branch always evaluates to 1. But the problem is up here. Once x1 evaluates to 0, kind of regardless of what I put in x2, it could be 0 or 1. It's enough to find 1, but it doesn't matter. Because I want this to be true for every value of x3, there is going to be one value of x3 that won't help us, okay? Because anyways, we had x1 to being 0 here. So this 0 will make the whole thing false, all right? Anyways, when you're trying to prove that a fully quantified Boolean formula is false, it's a bit awkward to do it directly. Really, you should just flip all the quantifiers and then the formula, and then you can prove it as if it was true. But you can still, if it's small enough, you can still reason through it even directly, okay? Is it clear how fully quantified Boolean formulas operate? Okay, we're just basically asking at each branch either that one of the two sub-branches evaluates to true or both of them, and kind of you recursively evaluate it all the way up top. Okay. All right. So, for example, we can view the class NP as a fully quantified Boolean formula where all the quantifiers happen to be existential, okay? So there exists x1, such that there exists x2, such that there exists x3, blah, 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 such that the Boolean formula is 1, right? And co-NP, you can view it as for all x1 and for all x2 such that blah, blah, blah equals 1, right? So these are like opposite special cases, okay? But in general, in a fully quantified Boolean formula, you're going to have alternating quantifiers, okay? And TQBF is the language of such expressions that evaluate to true, all right? And there's a fact, okay, and also we're going to assume that it's a 3CNF. And there's a fact that this language is PSPACE complete. If we have time at the end of the lecture, I may say a little bit more about this. If there isn't time, anyways, in the slides of this lecture, there is a proof that you can go through offline that TQBF is PSPACE complete, okay? Again, we may or may not get to it during lecture. Either way, they are part of the slides and you'll be able to go through it offline if you want to convince yourself of that. Anyways, this fact is kind of classical complexity theory. It doesn't really have to do with probabilistic proofs. It's just something that you may or may not have seen already. Any questions about what is a quantified Boolean formula and what is TQBF? Okay. Hopefully my audio is working. Great. So onwards. So now we have this TQBF. And that was our first step. And the second step is that we are interested to turn the kind of Boolean logic problem of deciding whether a formula is a QBF is true or not into some question about polynomials. Okay. So we want to arithmetize an expression such as this one. Now, intuitively, what we want to do is we want to arithmetize both the formula and the quantifiers. So we're going to somehow turn this into a polynomial, and we want these operators to be some operators on polynomials. Okay. Now, for the formula, we're just going to use the same arithmetization used for sharp SAT. Okay, the one that was a low degree extension. So we're going to transform the formula into an arithmetic circuit that agrees with the formula on every Boolean input. Okay, so this was the second arithmetization that we saw in the last lecture, right? And the main property is that, evaluating this arithmetic circuit takes us proportional to the size of the formula, and the total degree is not too large. Okay. Okay, so that's easy. As for the operators, well, you know, the for all quantifier behaves like a conjunction, right? So whenever we want to say for all xi, there is the same thing as saying, give me the formula with xi being 0 and the formula with xi being 1. And I want to consider the conjunction of these two because I want both of them to be true, right? So the universal quantifier on a variable is like taking the end of two copies of the formula with xi being 0 and xi being 1. But we have already seen how to arithmetize ends. That was just multiplication, right? So we can just define this operator, product of xi, which is going to replace for all that xi, and that's just syntactic sugar for this arithmetic expression of the polynomial. So when we write product xi p of xi, of course, there's other variables that are not being affected here. It is the same thing as writing the polynomial, taking the product of it twice, once with xi being 0 and once with xi being 1. All right. And again, right now, none of this is like justified yet. We're just taking educated guesses given our experience with arithmetization so far, right? It was useful in the past to replace ends with products, and we're doing the same right now. Okay. The existential quantifier behaves like a disjunction, right? When we're saying there exists xi such that this is true, it is as if we take two copies of the formula with xi being 0 and xi being 1, and we take the OR of the two formulas. And so we already saw last time that there is a way to arithmetize kind of conjunctions, which was taking this expression, or in fact, last time I wrote it a little bit differently, though it is the same expression. Last time we wrote x plus y minus x times y, but that's the same thing as, 1 minus x and 1 minus y, right? So we can define an operator, let's call it coproduct. It's like flipped over a product on the polynomial to be this other arithmetic expression. Okay, and again, this is again just an educated guess of what it might be useful to do. Okay, we're just translating logical operators on the formula into arithmetic operators onto the corresponding polynomial. All right. All right. So in sum, our candidate arithmetization of this expression is this arithmetic expression over here. Okay. And it's not just a candidate, but it actually has some desirable property that because the polynomial agrees with the formula at every Boolean input, and this arithmetic expression plugs in only Boolean inputs into the polynomial, the two expressions are equal over any field. Okay? Because here I'm plugging in only Boolean inputs, and I'm just basically doing Boolean logic of like basically 0-1 arithmetic. Okay? So there's a well-defined sense in which this is an arithmetization of this one. Okay, so whatever value this has, if this one is 0, then this one is also 0. If this one is 1, this is also 1. Okay, regardless of which field we're using for the arithmetic. Okay, I'm going to pause for a moment. There is going to be some problems that come up in a moment, but for now, this is like a legit starting point for arithmetizing this one. Okay, like it has that a good property. I haven't had any questions so far, so it'd be good to somebody step in. Yeah.
Could I ask just for like, how do those two, like, how does a conjunction followed by a disjunction look in like tandem?
Yeah, well, so once you have applied, let's say you have applied this operator to this polynomial, right? Now you have this, you have produced this other polynomial. Let's call this polynomial p prime, right? Well, the next one over, it's going to be applied to be p prime, right? You're just going to apply it to, right? It's an operator, right? So whatever is the polynomial that was produced by the previous operator, you apply that to it, right?
Okay, so you work from right to left, going outwards.
Yeah, exactly. So,
Okay.
like you first you apply this operator to it, right? Then this one will be applied to this whole thing, right? This one will be applied to this whole thing, right? So you will see that the thing is exploding, right? Which makes sense, right? In some sense, this was also exploding, right? This is a crisp or a short description of a big tree, right? In some sense, this also is, right? So as you apply operators from right to left, you know, the polynomial to which you're applying things becomes bigger and bigger, right?
Is the increase of the degree not kind of like prohibitive for efficiency?
It sure is, and we'll have to tackle it. But right now, we haven't talked about it yet. But yes, we'll have to deal with the degree. But for now, before we deal with the degree, like even before the degree, like these are like equivalent expressions. Okay. So there's a question by Tal about, you know, why when we discussed sharpsat, did we have to worry about the field size? And here we don't. Well, the difference that in sharpsat, we were counting the number of satisfying assignments. So therefore, we had to talk about like some integer, right? And even to talk about an integer, we need the field to be large enough for us to be able to talk about that integer, right? And that integer was something between 0 and 2 to the n. But here we're not counting anything. We're just we're just deciding, does it evaluate to true or false? So because we don't have to deal with any integer other than 0 and 1, we actually don't care about the size of the field at this point. Later on, when we run a protocol, we may have to care about the field because we might have to send randomness to the verifier, and we may have accumulating errors, and overall we may need each round's error to be small enough so that we can absorb each round, right? But for unsat, we did care. Yeah, you could say that for unsat, for the precise arithmetization, we don't. No, for unsat, we also care, right? Because if we apply the precise arithmetization to unsat, it will still count, right? And if you pick a field that will cause overflows, that will cause a problem, right? Here, we're not adding up anything. We're not counting any integers. We're just always asserting, is it true or false? Okay. So in both of the previous examples in the last lecture, we did care about the field size. There's another question about, does it matter about the x plus y? sort of minus x times y versus this one, well, they're the same thing, right? So if you open the parentheses, you get the same thing. So it's just different ways to write the same thing. Great. Good questions. Any further questions? Okay. So now we start thinking about, okay, so we have this arithmetic expression. We want a protocol to evaluate, to help. We want a prover to help the verifier evaluate expressions of this sort. So imagine the verifier has an arithmetic circuit for this polynomial, and the prover just wants to prove that this expression is either 0 or 1, right? Usually 1, okay, but it doesn't really matter what it is. And you say, well, we don't have much to use here. We've seen 2 interactive proofs total so far. One was for GNI, which doesn't sound very useful. And the other one is the sum check protocol. So we're going to try to take inspiration from the sum check protocol. Now, we can view the sum check protocol as basically dealing with n operators, right? If the sum check protocol is about an expression such as this one, sum p over the Boolean hypercube, that is as if we have this n summation operators and we're kind of peeling off them one at a time, left to right, right? Because we start out by fixing the first variable, and then we are left with a subproblem that has n-1 operators. And each round of the sum check protocol is kind of dealing with one of these operators until we get to the end, where we can do a consistency check against the polynomial, right? So this is one way to think of the sum check protocol. So we could say, all right, like let's just kind of follow the idea. And we could say the first round of the new protocol that we design, the honest prover is supposed to send this expression, but for x1, right? That is going to be a univariate polynomial, of course, right? Because each time you put one of these operators, the variable disappears, right? So if you peel off the first operator, that means that x1 is still around, right? Because it wasn't producted away, right? So this is this expression, but for the first operator. This is a univariate polynomial. But the problem is that, yeah, we could send this polynomial to the verifier, but it may have enormous degree, right? Because think of x1, for instance. x1 survives every operator from here until the end, right? And each time you apply one of these operators, which are making some other variable disappear, x1 is going to be multiplied and maybe double its degree, right? And then double its degree again, and then double its degree again, right? And in fact, maybe it didn't even start with degree 1. It might have started with degree maybe 3m, in case, I don't know, x1 appears in almost all of the clauses, right? But even if it started with like a small degree, like still, like in each round, it's going to be potentially doubled, okay? And that's problematic, right? Because the verifier cannot afford to read a polynomial of exponential degree, okay? It's just too long to kind of send this message. So before I continue, is it clear what the problem is? Notice that here in sum check, it was not an issue because this is a linear operator, okay? And the linear operator doesn't mess with the degree. The operators that we have here are both nonlinear. The product and the coproduct both cause a multiplication between P and itself, right? Whereas here, the summation operator is a sum between P and itself, right? You sum P with one input plus P on the other input, right? But that doesn't change the degree. And here I am talking about individual degree because this is a univariate polynomial, right? So there's a question about by Vahid on so we did arithmetization last time. Yes, because we wanted to count, but because we wanted to solve a problem. Okay, in that case, it was counting. Now we want to solve some other problem, and generally speaking, in the world of probabilistic proofs, polynomials are your friend. So whatever problem you want to try to solve, is generally a good attempt to try to rephrase your problem to be a problem about polynomials, okay? So, you know, we're trying again to say, well, polynomials work last time, we'll try again. Even though we're not counting, we're doing some other task, okay? So, and more generally, the term arithmetization is not well defined, but it's sort of suggestive term for any process that translates something combinatorial, Boolean logic, about problems into algebraic problems, okay? Like usually about polynomials, okay? And yes, here I'm writing PI to talk about, I mean, in general, you have, I mean, we were talking about P1 here, but in general, PI may have degree 2 to the n minus I because it went through n minus I doublings of degree. And of course, P1 would be the one that has the largest degree potentially because it went through n minus 1 doublings through xn, xn minus 1, blah, blah, up to x2. Right? All right, further questions about this point? Okay, so so we have a problem that the degree is too large. So we're going to tackle it with a technique that is about degree reduction. Okay, we're going to bring in some other, let's say, a new idea. Okay, that is going to enable us at the cost of more rounds to basically reduce the degree whenever it increases. Okay. So here the rough idea is that we only really care about what happens on the Boolean hypercube. And on this very special Boolean domain, many polynomials behave the same. So for example, this multivariate polynomial with all kinds of degrees has the same value as this other polynomial, where what we have done is we took any degree greater than 1, and we just formally replaced it by degree 1. Okay, obviously we're not introducing new monomials, it doesn't make sense, but any variable that appears, for example, x1 cubed, we just take the exponent, it is positive something, maybe it is already 1, or maybe it's 3 or 10 or whatever, and we just set it to be 1. Okay, so we can just take a polynomial and replace any power to be 1. Okay, why? Because these two polynomials agree everywhere on 0, 1. Why? Well, you know, when you plug in 0, 0 to the whatever power is still 0, and 1 to whatever power is still 1. Okay, so they agree. And why is this observation interesting? Because ultimately here, this arithmetic expression was only ever interested on asking what happens on Boolean inputs. Like truly, that's all we care about. Okay, so we're going to define a new operator, a downward triangle xi, that is a formal operator that takes a polynomial, and if it ever finds the variable xik where k greater than 0, it will replace it by xi. Okay, it's just like a syntactic operation that you look at a polynomial and you have a particular variable in mind, you go through and you just set to 1 all powers of that variable that appear with some positive exponent. Okay, so this is the degree reduction operator. So what we can do now is we can consider a new expression that has the same value as the old one, but it does not have this degree problem. So what we're going to do is we start with the original polynomial, and first, you know, for good measure, we just linearize every variable, right? Because maybe this one x1 comes in with degree, I don't know, 5, because maybe x1 appears in 5 different clauses. Okay, and we just say, well, you know, whatever, we'll just kind of we'll just set to 1 all the degrees right away. Okay, and then every time we have either a coproduct or a product operator, well, we again set to 1 all the remaining variables, right? Of course, we don't need to set to 1 xn because xn now is gone. but we can set to 1, x1, x2, x3, blah, 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 xn minus 1. Their powers will be set back to 1. Then we just keep going, right? And of course, as we go left and left, there are fewer and fewer variables left. So in between these product and coproduct operators, we have fewer variables to linearize, okay? By linearize, I mean just set the degree to be 1. And this expression, even though it's much uglier, it has the same value as this expression, okay? Because the only difference between these is that sometimes we're swapping out a polynomial for another one, but crucially, they agree on Boolean inputs. So we are not changing what the next operator would have done on Boolean inputs, right? All right, this is a subtle point. We're just going to slow down for a moment. And, does anybody have questions about this? Okay.
So just one quick question. So in this case, in order to reduce the degree, I guess we also need to expand product and sums, maybe. So does it mean that the expression in the end has anyway like an exponential number of terms? Like for instance, if I get like I minus 1, the product over I, expanding this term, I would get like exponential many terms.
Yeah, it does mean that. Unfortunately, it's not our problem; it's the prover's problem, which right now, we are not caring about because anyways, the prover is going to be proving us something that is PSPACE complete. So it's already going to have to work hard, and so that's okay. So here, in order to detect whether a variable has degree greater than 1, and we need to do something about it, and what are we going to do about it? It may, in general, require opening up the whole expression and then doing the operation on that. Okay, but that's okay, right? As we'll see, the verifier will be doing none of this. This is all in the prover's head. Okay, good question. There's a question I was saying about, are we saying that QBFs have alternating quantifiers? They may, okay? And so we can either enforce that they're alternating. That's one way to do it. And of course, if they're not, then you can introduce additional variables and make them alternate. Though in order to prove PSPACE completeness of TQBF, they will have to alternate, okay? That's kind of comes up from the proof. So, and this is not surprising because when they don't alternate, you get things like CoNP or NP, and those are not as powerful as PSPACE, believed not to be. So kind of the power of alternation is what sort of captures the power of PSPACE. Now, for simplicity, here I show them as alternating, but whatever protocol we're going to write won't actually care. So if you have some expression that looks like product, coproduct, or coproduct, product, coproduct, doesn't really matter. There will be just something to be done for each operator. And similarly here, even the fact that we're putting a kind of degree reduction operators in this very regimented and systematic manner is just for notational simplicity. You can just, I don't know, put them half the time, because anyways, what you care about is for the degree not to blow up. But if it blows up to size 8, well, who cares? It's still a constant, or even something polynomial for that matter, right? So, but you need to put them enough so that it doesn't become super polynomial, right? So you have quite a lot of latitude in terms of where to put these things. It's just nice notationally to put them in some symmetric way. As we'll see, the protocol just won't care. It has something to do. It just goes operator by operator, and there's a subroutine to do for each operator as a function of what the operator is. More questions? A couple of comments. So arithmetization truly is, more of an art than a science, in the sense that, I don't know like a systematic way to talk about all useful arithmetizations out there. It's really just some sort of set of tools and techniques and intuitions that plays a really like enormous role in probabilistic proofs. And in fact, not just. There is some well-defined sense in which Gödel's incompleteness theorem is through arithmetization, and sometimes it is credited as the first arithmetization. Also, lower bounds, circuit lower bounds are where it was used even before probabilistic proofs. So in the paper that introduced the sum check protocol, and then it cites these prior papers on circuit lower bounds where it was first introduced, let's say in computer science. But it's a very deep and in retrospect, natural, but sort of a priori not clear at all thing to do, to translate Boolean questions into problems about algebra. I mean, once you know that polynomials are very useful probabilistic proofs, then it makes sense. But a priori, it's not clear at all. Very beautiful set of tools. All right, so now we have a new expression. Here it is that has the same value as the old expression, but now we have, like, if you look inside halfway through these operators, we don't have degrees blowing up. So we are left to design a protocol that will kind of systematically peel off one operator at a time, ideally with some error that is not too big, so that overall, if the error is, say, in each round on the order of 1 over the number of the operators, then we can get to the end of peeling off all the operators with, say, constant soundness error, okay? So that is what we're going to do now, and that is Shamir's protocol, okay? So this is the expression. I just copied it from the bottom of the previous slide. We want to check that it is either 0 or 1. Doesn't really matter. Let's just call that initial claimed value to be some gamma 0. Okay. And so how many operators do we have? We have we have the original n product and coproduct and so on and so forth. And then sort of we are adding n reduction operators, then n-1 reduction operators, then n-2 reduction operators, and so on and so forth. So that is the sum. Okay. So sum of I from I to n. And that gives you roughly like, n squared operators. And we'll just peel them off one at a time. Now, one of the confusing things to talk about Shamir's protocol compared to the sum check protocol is that the round number is not the same as the variable that you're discussing, right? Because if you have n operators and you're peeling off n variables, then in round I, you're discussing variable I. Now you have k rounds, but n variables. So in some round I, there is some variable ji that you're discussing, okay? So this is just some confusion that usually comes up. So we have now k rounds, and we can view it as, rather than writing this enormous protocol, we can just view it as basically as a sequence of reductions from one claim to another. So we're going to have k rounds, and in round j, we're starting with some claim that abstractly looks like this. We have some operators left. We had a total of k operators. We are at round j, so we have we're starting from a jth operator, right? But of course, the other operators O1, O2, blah, 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 up to oj-1, we have already dealt with them. And by this time, we have some sort of a claim that we got to, where rather than claiming that we want to claim that this expression evaluates to gamma 0, it evaluates to some gamma j-1. And again, when j equals 1, then this is the expression we started from, okay? And what's going to happen is that the prover is going to send some polynomial, the verifier is going to send some randomness, and we're going to reduce to a simpler claim. What does it mean as a simpler claim? Is that we have one less operator, and potentially there is a different kind of value that we're claiming, okay? So abstractly, this is what's happening. We're going to have kind of k one round reductions, and each of these one round reduction is going to reduce a claim with this many operators with one less. By the way, you can view the sum check protocol this way as well, okay? Like last time we discussed as one big protocol, but I can also describe the sum check protocol as n one round reductions, okay? Between smaller and smaller summation claims. The sum check protocol is simple enough that can just be written down all in bulk. Shamir's protocol is not so much. It's a bit awkward to write it in bulk because you don't have always the same operator. So it's easier to write it in this kind of iterative fashion. All right, so before I continue, let me just look at the question. So is the new expression also the lowest possible degree extension, or can we get an extension of even lower degree using a better arithmetization? Not quite sure I understand that question. Maybe it's about this one. And so I think that if we take this part over here, then that is, I think, a multilinear polynomial. And I think it's as good as it's going to get over something that is over 0, 1 to the n. Okay, so I think it has minimal degree. But then, you know, that's anyways just part of the expression, right? Things continue. Okay. So things get more. So I wouldn't know what to say about later. But you know, this part over here, once you've applied those operators, there is a multilinear polynomial, and it's kind of the same as had you uniquely extended the function on 0, 1 to the n. Okay, so hopefully that addresses the question by Matthias. There's a question by Meet about the order in which we open. So if you remember in the sum check protocol, we were going from left to right, but you say, well, what does it mean? In the sum check protocol, the operators commute, okay? And you say, yeah, I guess in the sum check protocol, the order doesn't matter, right? Because the operators commute. Here, the operators do not commute, okay? And it is important that we start from left to right. And the reason is that the point is that we kind of, when we deal with an operator, it is an operator that is fixing the variable, right? This one, for example, is fixing x1 to be 0 and 1 simultaneously. And when we remove it, we're left with x1, right? And we're going from basically the most complex statement to the simplest statement. And if you look, as we move from left to right, the statement that we have gets simpler and simpler. In the extreme, this statement we can evaluate ourselves. Okay, so this is the correct direction. We're going from the big tree to a smaller subtree, to a smaller subtree, smaller subtree, and so on and so forth. So this is the correct direction, this way. Okay.
I have a question.
Yeah.
If we had opened from right to left, even then we will be getting some more complex to simpler statements, right? You are eliminating variables as you are going from right to left.
I don't think it's well defined to eliminate from right to left. So you will get like, I'm not sure how to do it. It's not.
So the examples that we took, the simple examples for arithmetization, we did open from right to left. Like when you define these product and co-product operators, you said that the openings will be done from right to left.
Amit, I'm sorry, I do not hear you very well. If there's like a static and maybe the mic, can you please repeat maybe slower and if you can more clearly?
Sure. Can you hear me now?
Okay, go ahead.
Yes. So I was just saying that when you define the product and the co-product operator, you said that when we compose them, it will be the right operator that we'll apply first, and then we'll go towards the left.
Yeah.
So I'm just wondering why is there a problem to go from right to left?
So there are different things. So one is the precedence of how operators are applied, right? So they are applied kind of like this, right? And this is, you know, usually what is understood when we sort of write operators kind of onto functions, right? But differently from that, there's a protocol question, okay, which is how does the protocol go? And what we want to do is we want to go from complex statements to simpler statements, all right? So here we have the biggest statement, the most complex, that is easy to tie to the final thing, right? Here we are tying, the verifier will have an easy consistency check from the end to here, right? when you peel off this one, right, there's going to be some consistency check against the gamma 0, and then it can continue, okay? So I don't know syntactically how to start from here. Like, I don't even know what is the consistency check starting from there, okay? So there's, yeah, like it's hard to describe things that, you know, like I don't think exist. But again, if you sit down to give it a shot, it's like not clear what does it mean to start from here. For example, on the left here, you have just one variable and you're going to fix it at a random point. If you start here, you have a bunch of variables. What do you want to do about them? If you give them all random points, now the prover knows those points, okay? Whereas here, like, first he committed to the first univariate polynomial, and then I send the randomness to fix that variable. So I can do a consistency check with the polynomial identity lemma. So the other way around, it's I don't know, like, it doesn't make sense to me. I don't know if I mean, I'm trying to communicate intuition, okay? Hopefully it helps a bit with that direction. All right, so then there is a question by Ida. How opening the degree reduction operator works. So we haven't discussed yet how to deal with any of these operators. We will in a moment, but is it at least clear what the operator is? All right, so we haven't discussed any of these yet, so we'll discuss in a moment. Okay. So the operator here, I mean, it's real, right? It actually is swapping out a polynomial for another. Okay, so we do need to process it. Okay, it's not just just in our head. This operator, what it does, it takes this whatever polynomial is here and replaces it with another one. So when we travel in this direction, we're going to have to tie the polynomial that is obtained from this operator from the polynomial that was applied to, and we're going to have to tie those polynomials together. So we do have to process it. Okay, but now maybe we're getting ahead of ourselves. Let's talk about what's the protocol itself, right? All right, well, first at the very end, whenever you're done, you're gonna finish up with a claim that there's no operators. P is going to be claimed to evaluate to something at this point, okay? And then the verifier just checks it, all right? So the question is kind of what happens here. So in every round, the prover is going to send a univariate polynomial. This is just like in a sum check protocol. And remember that because we are in round J, there is a variable ij between 1 and n that is the variable that is kind of pertinent to the operator oj, right? For example, here, let's say when k equals 3, right? Not k equals 3, when j equals 3, when j equals 3, the variable here that we have is ij equals 2, right? I don't know, when j equals, what is this? 1, 2, 3, 4, 5, 6, 7, then ij is going to equal 1, right? Because it's this one here, okay? So at the jth round, we have some pertinent variable, okay? Let's call that variable ij. And in a sum check protocol, what was happening in each round is that we were taking whatever the prover was sending and we were checking it against the previous claim, okay? So this, of course, this consistency check will depend on the operator, and we'll open that in a moment. But the point is that after we do this consistency check, we're going to send a random field element, okay, associated to this variable ij, and we're going to take the polynomial that the prover sent, evaluate it at random, I mean at this point, random point that we picked, and this is how we're going to generate the next claim, okay? And then we're going to basically set a kind of the latest value for the variable guess, how to say, maybe there should be a J here, and I should say new and old, sorry. Let's say current, new, right? Or okay, I guess it's not written very well here. But basically what I'm saying is that maybe the variable ij was already fixed to some value before, and we want to replace that value to be like the one that we just freshly sampled, okay? And we'll see why in a moment. In the case of the sum check protocol, it was kind of clear that, you know, at every point, whenever you fix a variable, it hadn't been fixed yet, okay? And so you just fix it to be the value that we sampled. In this case, it could have been that was fixed before, okay? And then we just replace that value, okay? So now let me open up this one. So this one depends on what is the consistency check? Well, it depends on what the operator says. For example, if the operator says it's a product, then the consistency check between what the polynomial the prover sent and the previous claim is this one. We just apply the product operator. So we take the polynomial, pj tilde at 0 times pj tilde at 1, and we just check whether that's the previous one. This is entirely analogous to how in the sum check protocol, we were checking something like this. Okay, I cannot write anymore there. Okay, it's entirely analogous to that, right? We just apply the operator. In that case, it was the sum, okay? And we check it against the previous gamma j minus 1. We didn't give it a name to gamma j minus 1, but it was the previous polynomial evaluated at whatever point it was, right? And indeed, you see here that this is what happens for the next round, okay? What if it was the other operator, the coproduct? Okay, well, we just evaluate whatever expression it was and check that instead, okay? And what if it was the degree reduction operator? Well, again, there is just some expression for that. It's just slightly more subtle. We're going to apply the reduction operator to the polynomial, and then to the resulting polynomial, we're going to compare it, we're going to evaluate it at the already fixed value and check it against gamma j minus 1. Why is it already fixed? Well, let's say, for example, that we're looking at this degree reduction operator, okay? Now, let's say we have processed this one, okay? So we have fixed x1 to be some random value, right? In the first, when j equals 1, right? Now, when j equals 2, the variable that we're again processing is 1, like x1, right? And our goal is to link the polynomial that is here and the polynomial that is here, right? Now, this polynomial, we already have fixed an omega 1, okay, for the old one, okay? And so that is why that we need to use it here to link it to the previous claim, okay? The previous claim here being, in that case, would have been P1 tilde of, I don't know, omega 1 old, okay? So this is not a polynomial identity test. This is a consistency check, okay? All right. All right. So we haven't said, I mean, all of this is just describing the protocol from the verifier's perspective. We haven't talked about what the prover does, and we haven't even analyzed anything, neither completeness nor soundness, okay? So this is just to specify the protocol. What we're going to do now is we're going to look in detail at this one and that one. This one is anyways the same as the previous one, okay? Now, let me just pause for a moment and see what the questions here. All right, there's a question by Jenny about wij plus 1. Now here I am replacing the old value by the new one. So I'm not wanting to talk about ij plus 1. I'm just trying to replace whatever value the variable xij had to the newly sampled omega ij. Okay, that's what this means. I'll fix it a bit more explicitly in the slides. In the left to right arrow, this one here, this is a single x, okay? it's a single X, and maybe I could be, again, slightly more precise. And right here, it's an Xij, right? It is in the variable Xij. And also PJ tilde, what are they claimed to be? Oh, well, the PJ tilde, we'll see them in the next slide, what they are. And yes, Wij is the current stored value of Xij. Yes, and unlike in the sum check protocol where you go from unbound to bound and that's it, here you will be bound multiple times as a variable, okay? Because you'll be switching between different polynomials that have the same variables. Again, and we'll get to Amit's question later, because in some rounds the polynomial will be set, the polynomial sent will be higher degree than other rounds, and this will influence the soundness analysis. But hopefully, at least syntactically, things make sense. Are there any syntactic questions? We still have to analyze this protocol, but is at least clear what the protocol syntactically is? I hope nobody's speaking because I don't hear anybody. All right. Right. By the time we're done with this, the sum check protocol will look very simple.
Sorry,
yeah.
one question. Can you say again what is that? I'm getting confused in this omega ij equals to omega ij where you have assigned. Can you say again what's happening? I'm getting confused.
Yeah, so I'll clarify it in the slides before I post them, but what this parenthesis is trying to say is that we sampled omega ij as the new value, the new random value for the variable xij. And this parenthesis is just saying, well, set it to be so. Okay, or like in case you already had a value, just replace it. Okay, and I'm not quite sure why I wrote that specific set of characters. It's really not clear. I'll just write it in English to be more precise. But all it's just saying is that we sampled omega ij for the variable xij. Well, you know, let it be this one onwards until it gets overwritten next time, right? Great.
I have a quick question about that. So like, say I strip off the very first product, which relates to x1.
Yeah.
So I sub 1 is 1, right? So I set a random value for omega 1, and then the next thing also deals with x1, and I set a new value for x1, like maybe it's 0 now. I don't understand why this doesn't mess up like the consistency of my piece of J tildes.
Okay, well, we will analyze it in the next slide. Also, just something that I wanted to so you mentioned 1 or 0 as random variables. They're actually as random values. They're going to be random values in the whole field. Okay, so the way maybe to think about it is that, I mean, the first round, omega 1 is set to be, I don't know, this value, right? And the next time around, let's call it omega 1 prime, it's going to be, I don't know, this value, okay? They're not sampled just between 0 and 1, they're sampled between the whole field, okay? Now, regarding completeness, which is your question about basically why does this work? Well, I have an entire slide for that, okay? And Amit has a question, is it correct to say that in the jth round, the proof ascends univariate polynomial on xij? Yes, I will add this in the slide as well. And let me make a note, and I'll make it clearer in the left to right message that it takes xij. Okay, great. Any further questions before we move on? So we haven't analyzed it yet. Okay, so let's maybe go through analysis. So we're going to go through a careful analysis of this one, careful analysis of this one. Okay, and when we go through this one, hopefully it will clarify the completeness question that Jenny made. All right. So consider around J where the jth operator is product of xi, and I'm dropping xij just for simplicity. And this whole slide, like you can just mechanically translate it to be about the other coproduct. So we won't go over that. So completeness, we're saying, suppose for a moment that the input claim is true, namely OJ, which is pi xi, and the rest really does equal the claimed value gamma j minus 1. Now notice that because ij is this I, right? The things that have already been fixed are things to the left. So we do have values already fixed for omega 1, omega 2, so for x1 and up to xi minus 1. And the value for xi hasn't been fixed yet, because this is the first time we encounter xi. Okay? So xi here is free. So the honest prover is going to send this expression, but for this one, like it's going to remove it, right? It's not there. Like it peels off the operator, and the honest prover is supposed to send whatever polynomial this is. Now, what is that polynomial? Well, remember that all the other variables are kind of knocked off by other things here. So this is a univariate polynomial in xi. Okay. Now, first, because the honest prover sends this polynomial, the verifier's check passes, because the verifier checks this. But like if you apply this operator to this expression, which is this thing, you're going to get that one, which is what the verifier checks. Okay, great. So the verifier's check passes. Now, for every choice of randomness by the verifier, the new claim gamma j, which is set to be pj at omega ij in the previous slide, really does equal to this one, right? Because this whole expression is pj because we defined it right here, right? So this is saying that the new claim that is produced is correct. Okay, so we're going from correct claim to correct claim with probability 1. So input claim is correct, implies output claim is correct, with probability 1 over the choice of the randomness of the verifier. Okay, and there's just maybe more notation on what is happening. All that's happening is the prover says, "Okay, I've peeled off the operator." The verifier says, "Okay, well, yeah, I checked it. You peeled it off correctly. Good job." And then the verifier outputs a random claim for this polynomial evaluated at a random point. And so if you remember in the previous slide, the new claim here was this expression minus the operator equals whatever the prover sends at the random point. And here we just proved that that expression here, which is the new claim, really is true because we started from a true claim and the prover sent the correct polynomial. Okay, this is exactly what happens in the sum check problem. For soundness, you can say, well, suppose the original claim is not true. We would like to show that with high probability over the verifier's randomness, the output claim is also not true. Okay. So let's say the prover sends some polynomial. And now notice that in this round, we actually do expect a polynomial of degree at most 1. Why? Because this operator here is after all the reduction operators. So we do expect that when you peel off this one, the degree of in xi is 1. Okay, so we are expecting some polynomial of degree 1 by the prover. Let's call that pj tilde. Now, like in the sum check case, we have two cases. Either this polynomial is the one that the honest prover would have sent. Okay, let's call it the honest polynomial. But in this case, the verifier's check fails always because we're starting from a false claim, and if you send the correct polynomial, then you really won't get gamma j minus 1. So this check won't pass. So pj tilde of 0 times pj tilde of 1 won't equal gamma j minus 1 because this one doesn't, and these two are equal. Okay. So this is kind of like the stupid prover. This is the prover that if it sends pj, it knows in this case, the verifier will always reject. So let's say the prover sends just something else, some pj tilde that is not pj, okay? By the definition of the honest polynomial, we do know that this expression evaluated at omega ij really is the honest polynomial evaluated at omega ij. But however, the verifier decides the next claims target, gamma j, to be the evaluation of pj tilde at omega ij. So this is saying that the output claim is tantamount to comparing these two polynomials at a random point. But these are distinct polynomials. And so the probability that we have a correct output claim is at most 1 over f, with probability taken over the choice of the verifier's randomness. Okay. So that's it. This is the analysis of the product operator. Okay. It's very, very analogous to what happens in the sum check protocol. In the sum check protocol, that we had this event that was saying, is it the case that you're sending the honest polynomial in the bad case? If you are, then given that your input claim is false, then you certainly will lose. Okay. But if you send something different, then it means that kind of your lie will propagate. Okay, with high probability, because your output claim is essentially is tantamount to saying these two polynomials are distinct, agree at a random point. Okay. All right. So I'm just before we go to the degree reduction operator, I'm just going to pause for a second, and you know, I know notation is a bit kind of challenging, but you know, I'm not quite sure it can be improved very much. All right, so there's a question about honest. So honest is well defined. It is basically this expression here. That's the honest polynomial. That is pj. That is what the honest prover would have sent. Okay, so that is what pj is. So hopefully that answers your question, Bogdan. pj is that polynomial over there. Basically, in both the sum check protocol and in Shamir's protocol, you can run the honest prover strategy in a well-defined way, even when there's a false claim, because the honest prover is instructed to peel off an operator and send whatever polynomial is left.
I'm sorry, can I ask my question in voice? Because what I feel is that as opposed to the sum check protocol, where we only cared about honest polynomial, here we should be care about the honest pair of polynomial and gamma, because gamma is changing, right? If you care only about honest polynomials, then what you were saying before was incorrect, because honest polynomial was sort of like dishonest gamma.
The prover doesn't send gamma. Gamma is set by the verifier in the previous round. So there is no honest and dishonest gamma. Gamma is always honest in some sense, because it is computed by the verifier following its instruction. So gamma is always the previous polynomial sent by the prover evaluated at the next randomness. Okay.
Okay.
And the main difference in analysis of sum check and here is primarily syntactic, is that here we are taking this, like, is the claim so far false? Yes or no? If it is false and the prover sends the honest polynomial, then it will reject right away. If it sends some other polynomial, then it means that the claim will be propagated to be false with high probability. You can do the same analysis for some sum check, it's just that we didn't do it that way last time. So here's maybe an exercise to kind of carry out this type of round by round analysis onto the sum check protocol. And you can like really like syntactically translate this entire page to talk about sum check. All right, there's a question here. This numerator here is 1 precisely because of this 1 here. Yes, that is the degree 1. So that's answering your question, Amit. And why is this 1 to begin with? Because we are after all the reduction operators, in particular, the reduction operator for xi.
Sorry, like I'm basically repeating my question once again. So how do we know? So you have this claim that if pj tilde is equal to pj, the honest polynomial, then the verifier's check fails, right? But
yeah.
To this to hold, we must be sure that gamma j minus 1, which the verifier has, equals to the honest gamma j, which is the honest polynomial computed at a point.
Not quite. We are starting from the hypothesis that the input claim is false. We're saying, suppose that this expression doesn't hold. It is not the case that the left-hand side equals gamma j minus 1, whatever that is, okay?
Okay, yeah, sorry.
Okay, then if the prover sends this inner expression, then the verifier is just basically completing the last operator and comparing against the right-hand side, but by hypothesis, these things don't equal. Right?
Okay.
So then the verifier will definitely reject.
Okay,
so,
got it.
Great. Yeah. Sorry, maybe I didn't say it super clearly, but I hope it's clear now. So the only kind of, let's say, smart option for a prover is to just send something, anything else, really, right? But in that case, it's basically saying that the output claim is false with high probability, and then it basically propagates our hypothesis. Okay. And so this kind of round-by-round view of Shamir's protocol is basically saying, look, in the soundness case, you start from the original claim that is not true, okay? And then in each round, you have a chance that the prover flips from false claim to true claim, but it's a very small chance. With high probability, in every round, you go from false claim to false claim to false claim to false claim. Just the claims become simpler and simpler until you get to the last claim being false. You can check it yourself, okay? Great. Any further questions about this one? And then, 5 minutes, we should be able to do the reduction operator. Further questions about this slide? All right. So this is probably, I don't know, the most technical lecture of the whole week. So I think it will go down. It will go simpler from here. Great. Okay. So now we have. So that was an analysis of the product. The analysis of a coproduct is basically the same. Let's look at the reduction operator. Okay. So we have some round J, where the operator that we want to peel off, that we are peeling off, is this reduction on xi. Okay. So let's first look at completeness. So now the expression that we have looks like this. Notice that we are dealing with xi, right? But xi has already been given some value, okay? And you might even wonder, like, wait a second, what does it even mean to apply this operator to something where the value of xi has already been applied? Well, this is just syntactic sugar for saying, don't put any values, consider the whole thing as a formal expression in all the variables, where of course the variables that are kind of knocked away, don't survive, but all surviving variables, keep them around, apply the operator, and only at the very end put in the values, okay? So this is syntactic sugar that may be confusing for something that is certainly well-defined, okay? So, right, so this is, suppose this is the case. Now, what the prover is supposed to send, the honest prover, is as usual, the inner expression, right? But it will leave free xi, okay? Now, what the verifier's check is supposed to do, it will apply the reduction operator to this univariate polynomial, okay? And then put in the value that was there, right? And again, why is the prover not putting it in? Because it matters. Like, this is the same reason with syntactic sugar. You have to put in the values at the very end, okay? Now, for the other variables, it doesn't really matter whether you put them before or after reduction operator because it doesn't affect it, okay? But so this is the consistency check. And it passes because, the verifier is just basically completing whatever this inner expression was with this operator, okay? Now, for any choice of gamma ij, right, the new value for the ith variable, the output gamma j is set by the verifier to be whatever was received at gamma ij, but because the prover sent this expression, that is the right thing. Okay, so you go from a true claim to another true claim. The next one with one operator less. Okay, so and again, like it might be easier, like on a slide twice the size, to not use any syntactic sugar at all to see really what's happening. That's why, but I just put this bubble. Otherwise, it will become even bigger. Okay, this whole slide. Okay. So this is the completeness. For the soundness case, suppose that we start from a claim that is not true. Okay. And the prover is going to send a polynomial that has some degree. Okay. Now this is before the reduction operator is applied, right? And what is the degree going to be? So I claim it's going to be either at most 3m or 2, right? Why? Because first it could be that we are in the innermost before any reduction operator was applied, right? In that case, we just have the arithmetized Boolean formula, and we have m clauses, each of them will degree at most 3, okay? And so any variable could have degree up to 3m, okay? So that's the innermost part. Or we are somewhere halfway through, in which case we had something that had degree 1, it got doubled by some operator, and so we have degree 2. Okay? So in the innermost case, we have 3m, and anywhere else, we have 2. Okay? But of course, the verifier knows which case it is because like these are like fixed rounds where it appears. And as usual, like either the prover sends the honest polynomial, in which case the verifier's check always fails, or it sends something else. But if it sends something else, it means that by definition of PJ, the left-hand side of the new claim is PJ at the new the honest polynomial at the new randomness. However, the verifier sets the gamma j, the new target of the claim, to be the prover's polynomial at the new randomness, which means that the output claim is tantamount to comparing these two polynomials at a random point, which agree with probability at most 3m or 2 over f, depending upon which round you're on. Okay. All right. So the way to, I think, work out this on paper, or that to kind of maybe to let it sink a bit offline, is to try to do the sum check protocol in this round-bound fashion. Once you're comfortable with it, you can try to understand the product operator better. And then maybe as a last step, this particular slide. Before I move on to the next slide, which is the last slide, are there any questions about how specifically this one differs from the product operator?
Just a short question. So we don't send a new challenge for each reduction operator, or? We
do. And it is this one here.
Okay, so if there are multiple reductions in a row, we have to do it, the same check over and over again. Because I thought it suffices that the prover sends one polynomial and then we put all the reductions into one check, but okay, it doesn't.
So in each round, we are dealing with one operator about some variable. In that round, we will receive a polynomial and we will send a randomness, okay? So all rounds in some sense look the same in terms of what's happening. The difference is that depending on the operator, you may have slightly different consistency checks. You may have slightly different expected degree for the polynomial that is incoming from the prover, right? And that's it, right? And so the differences in how we deal with different operators are in consistency check and the degree. But otherwise, whether it is product, co-product, or degree reduction, we're always assigning a value to a variable, possibly for the first time or possibly for the more than first time.
But could we compress all the reduction operators somehow into one check?
I don't know how to do it because, I mean, just like in sum check, maybe you can do two two reduction operators at once, right? That will kind of square the difficulty of that round. That's kind of what happens in sum check, but not really much beyond that, right? Like, because if you take too many operators at once, they will just blow up things too much, right? Each of them, they have some effect, right? Yeah. Regarding many reduction operators at once, it's a good question. So if you're asking specifically about reduction operators when they appear next to each other, that one is a good question. I'm not sure. Like I would need to check. Maybe it's a good question to look offline. Let's say if you want to do, here's maybe a good question. Okay, I would focus on the simplest part, which is all of these guys together, right? Which is like a pretty clear thing. You want to link the polynomial you have here from the polynomial you have here, right? Yeah. Possibly that can be done. I won't try to think about it right now, but I think it's a good question. So let me go back here. I wanna, before we kind of run out of time, I wanna get to the last slide, conclude, and then I'll come back to the leftover questions about this one. Okay, so I'll come back to your question, Ida. So just to conclude, overall, the completeness is that the way you reason about it, if you start with a true claim, then in each round, you propagate to a simpler true claim with probability 1 over the verifier's randomness for that round. And so in the end, the final check will pass because it's a true claim about the polynomial with no operators. Okay. And of course, at the end, how do you evaluate this one? Well, that is the arithmetization of the inner Boolean formula for the QBF, which you can do it by yourself as a verifier. Soundness, the total soundness, you incur, some error in each round. So the expression was like this, and you have 1 over f at each of the product or coproduct operators. Here you pay 3m because this is the cost, like you go from something up to 3m to 1, right? And then all the others are 2, okay? Because you're squaring something at degree 1. So overall, you have n things that are 1 over f, you have n things that are 3m over f, and you have a kind of this kind of a triangle of things 2 over f. And overall, you get an expression of this sort. And so you just need to make sure that the field you're working over is, let's say, quadratic in the relevant parameters. Okay. All right. So, and so this is basically telling you that from the very beginning, you should have arithmetized over a field that is large enough. Here, we're actually not using the fact that the field has large characteristic. In fact, you could potentially be working over a binary field, I don't know, f2 to the something, and just use the fact that f2 to the something is large enough, even though it has, say, characteristic 2. Okay, that's like something interesting that is happening in this protocol that was not happening in the protocols from the last lecture. Before I move to questions, I'd like to mention that there are additional slides that I'm not going to go over. It's primarily for your interest offline. There is one slide where it explains why TQBF is in PSPACE. Okay, roughly it's because you can process the whole tree in polynomial space. And then there are 2 slides on why TQBF is PSPACE hard. At a very high level, you start from a machine and you basically encode the machine's computation into a QBF. Okay, and there's like a very nifty thing that is happening on why alternation comes up. Okay, here's the alternation. So you see that in the proof of hardness, PSPACE hardness, you must use alternation. Okay, which you would expect, right? You wouldn't expect to only use existential quantifiers or universal quantifiers. Anyways, these things are part of the slides that I'll post. I think now is a good time for me to stop the recording and take on more questions.